Hello, I am Pranav. Today we are going to be discussing a topic known as learning with errors. So, this learning with errors is a foundational technique that we can use in post quantum cryptography techniques. So, as I have discussed in the last video, currently we are using many powerful encryption techniques like RSA and LGML for digital signature, etc. So these techniques are currently they are very perfect and they are very difficult to crack or break by attackers. This is because these sort of techniques, encryption techniques, are based on some mathematical problems known as hard to solve problems. So what it means is that, for example, RSA is based on a hard to solve problem known as prime factorization, which says that e even if you know a number, it is difficult to find the prime factors on which it was multiplied on. So, for example, in RSA, it will be a very large number, like some 200 digit numbers, which will actually be a multiplication of two different prime numbers. So, with those two prime numbers, in RSA, they will generate that large number. So, even if an attacker is able to get that large number, they cannot identify which two prime factors were used to form that such large number. So this we discussed last time. Uh, it is not exactly impossible to solve. It is just that it is so difficult to solve that it is not worth it. So that is the uh, goal of this encryption technique, because there is no such thing as impossible to solve problems. If it was, it will not be useful. If it was impossible to solve, then even the encryptor cannot encrypt with it. So it will be very difficult to solve without the private keys. So that is how these encryption standards work at their current level. But again, as we have said in the last video, with the advent of quantum computers and the Shor's algorithm, the powerful Shor's algorithm, which uses this quantum technology, we have identified that if we can use the Shor's algorithm, these currently hard to solve problems will be very easily solved. They will not be hard to solve problems anymore. So we saw how this source algorithm works. Currently, we do not have the technology to build such a powerful quantum computer yet, but in the future we will definitely be able to build such a computer. At that time, using the Shor algorithm, this RSA, LGML, which uses discrete log, prime factorization, every difficult to solve problem will be cracked. So, which means that while our current encryption standard is perfect now, in a couple of years perhaps it will not be perfect anymore. Then it will be easily cracked. So, our goal, the goal of the security field, is that we have to move to some other techniques which will be difficult to solve even for quantum computers. This is known as post quantum cryptography. This field, this will be our answer to those quantum computers in the security field. But the issue is that it is still a developing field. Our The perfect techniques have not been developed yet, but year by year, new and new techniques, new and new foundation, new and new bases are being introduced and verified and being tested time and time again, and eventually we shall reach some standards and techniques that we can use in the post-quantum world. So today we are going to be discussing one such technique, which is known as learning with errors. This is a sort of a foundational technique. So let us see what this technique actually is. So similar to normal techniques, we imagine we have private keys and public keys. So let's say I as a receiver has some private keys. Let's say four private keys. So these are those private keys. For example, then we will generate some public keys using the private keys, and these public keys are in the form of polynomial equations. It might seem different from normal normal techniques where we don't have these polynomial equations, but it will make sense. So we will generate some n number of polynomial equation such that the solutions for all these equation is actually our private keys. So this will be our private and public keys. So this private key will only be known to me, but this public keys is known to everyone. So before we look into learning with errors, we will see what is learning without errors. So imagine I only have just this, but the issue is that, as I've said, the goal of our encryption technique should be that the public answers should be very difficult to crack and find the private keys. But this, if you see this, and this is basic mathematics, these are all what system of linear equations, and it is very easily solvable. So since we have four variables with just this four equation, we can easily solve what are the values of our private keys. So this is not a good encryption technique because easily solvable. But that is not our goal. Here comes learning with error technique. So what we will do is, to these public keys, we will induce a small random error. This random error is a secret. No one will know this. This secret error except me. So these are some random error. So what will happen is that for our equation to the final answer, we will add some random small error to every single equation. And after that, so what will happen is that if we have this equation, okay, someone can solve it very easily. But imagine we add some error. This is solvable because it was engineered from the answer to the equation. So using reverse engineering, we can easily find this answer. But this is just a randomly generated equation such that there is definitely not a solution for all these equations. There is no single solution. But it is true that while there is not a single solution, generally they can identify some near solutions, some different near solutions that maybe they may develop private keys. But the issue is that they are very difficult to solve. That is our goal. As I've said, there is no impossible to solve problems, but our goal is to make it as difficult as possible. So by inducing these small errors, it is very difficult to find out what is the solution for all these variables. That is, what are the private keys? They can't find out because the equation itself is not actually correct. Okay, so we have a public set of public keys which they cannot find the private keys. Now, what actually shall we do with this? So let us see. Now, before we use this public keys, as per our encryption standard, this all our keys will be in a bounded accuracy, that is in a ring. This is known as modular arithmetic. So we add a mod. We will add a mod q to all our equations where q is a prime number. For this example, all our equations and all our numbers are small, but usually, just like RSA everything, the numbers will be very large naturally. So we will add a mod q to all these equations such that this will be our set of final public keys. So these are our public keys. So in this example, I have 10 public keys, say example. Now what shall somebody do with this public keys? So for example, a sender, they want to send an encrypted message to me. What will they do with this? So let us take a simple example. We will take bits of 0 and 7 1. As we know, any sort of message, any image, anything can be represented as 0 or 1. So if we can encrypt 0 and 1 securely, we can basically encrypt anything. So how we can encrypt zeros and ones? So we will see an example. So what the sender will do is that From this set of public keys, he will randomly choose some equations and he will add them. So here, let's say the sender took these three examples and he's adding them. Here with the errors, he will be adding them. So the final equation is something like this. But remember that since this equation is an addition of these three equations, the solution of these four, will naturally be my private keys. That is, the solution for that equation is also this. That is, this is a linear equation. So basically, since this equation for solution for these three is my private keys, so the addition of these three will also be the solution of these four. So this is with errors, with with the induced errors, but publicly these errors are not known. So what the sender will actually have, he will have this equation as his encryption. So what he will do is, if the sender wants to send the bit 0, he will just send this equation to me. But if the sender want to send 1, what he will do is, he will add 8. Where this 8 is coming, this is half of 17. 17 is our q. So we'll add half of that q value. Even he'll add it to the final answer, then he will send it to me. So basically, if you want to send 0, he will take some random equations, he will add it together and he will send it to me with the errors. If you want to if you want to send 1, he will take some random equations, he will add it, then he will add half of q, which is a prime number global variable, and then he will send it to me. So whatever he wants, zeros or ones, he will send some equations to me. Now I got some these equations. How will I understand whether I got 0 or whether I got 1? We will see. So imagine he, to this equation he send this, for 0 he send this equation, for 1 he is sending this equation. So as a receiver, I am receiving these two equations. Now what I will do, I have my private keys, and what we have known, the private keys were the solutions for these equations. So I will input my private keys into these equations. So for A1, A2, A3, A4, these are my private keys. So I will input these values into the equation I received from the sender. So from this, by inputting this value, I got some value. Then naturally we will add mod q. Then this is our final answer. Now we will compare. So by comparing my final answer to the received answer, we can see that the induced error, the answer is not same, but it is within 1. So by just adding 1, we can say that it will be similar. So what this means is that this error 1 is actually closer to 0. So because of this is not exactly same, but there is some induced error, because to our public keys, as we have seen here, we have induced some random error. That is the error we are getting there. But the solution, for our solution, there will be no natural new error. So what we will do that is that we will understand this is that natural error. But here the natural error is close to 0. That means while encoding here, the sender didn't add any number to the final answer. So this means that this received answer is actually 0. So from this equation, since that induced error is actually closer to 0, we can identify that the sender has not encoded or added any value to the final answer. So from this we can identify that the bit I have received is 0. Similarly, here we are receiving this equation. Similarly, I am inputting my private keys to this equation, and again the same, we are getting 5. But 5 and 14, what difference? It is has a difference of 9. So the induced error is actually 9. So 9 is actually closer to 8. What this means is that to the final answer, the sender has encoded or added 8 to it, which is actually half of 17, which is Q. So from this we can identify that since the sender has added 8 to it, naturally it means that he has sent the bit 1. So by identifying what that error is, and is it close to 0 or is it close to half of Q, we can identify which 0, is he sending me 0 or is he sending me 1. So this is the encryption technique. But only I will be able to identify this, because only I have the private keys which are the solutions for the 4 variables. Any other random person, they don't know what are the values for these equations. So they cannot naturally input this value and get the actual solution. If they Only if they have the actual solution, they may be able to identify what is the induced error and whether they have encoded what 0 or half of q. Without that actual solution, they will not be able to identify it. So naturally only me as the receiver with the private key will only be able to find out the actual solution, and with those actual solution and the received value, I can identify whether he is sending me 0 or whether he is sending me 1. So this is how learning with error works. Because of this induced error in our public keys, it will be very difficult for some intruder to find out what the actual private keys are. And with these error induced equations, only the person with those private keys and the solution will be able to identify whether it is 0 or 1. So naturally, since we are able to securely encrypt zeros and ones, we can basically encrypt anything, images, text, anything we'll be able to encrypt this. So how is this helpful in quantum, post-quantum technology? As I've said, the goal of our encryption technique is make it very hard for an intruder to find out what are the private keys. So this learning with error technique is a foundational technique. We cannot just use this as it is, but it is a very foundational technique that we can build upon, adding more techniques, adding more layer, or even combining other technique with this error inducing technique. One such example is in post-quantum cryptography, there is a lattice-based technique that is actually being developed and being gradually accepted as a post-quantum cryptography technique. So by combining this lattice and this inducing error technique, we may be able to build even more powerful or secure technique. So with this foundational learning with error technique, we may be able to build some more and more powerful technique. As this post-quantum cryptography technique is a still developing field, so more we need to find more and more techniques to refine our techniques, and this is one such example of our post-quantum cryptography technique. So that is it for today. Thank you.